I'm Brian Stuart, and I'm going to talk a little bit about various aspects of programming the Eniac. In particular, we're going to talk a little bit about bugs in some of the original programming for it. Now, when we talk about the Eniac, it's become somewhat cliche to talk about how different programming the Eniac was from programming modern computers. We always highlight the fact that you had to plug in patch cables and set switches. Well, certainly the process of deploying a program on the Eniac was quite different than punching cards or paper tape or typing at an interactive keyboard. But the process of creating the program, of determining the flow of control and the operations to be performed on the data, those weren't as different as we might think. And it's in that we're going to see that the bugs are also not as different as we might think. So let's go back to the very beginning of programming the Eniac. What was the very first programming done on it? Well, as you might guess, the developers of the machine also were developing some programming along with the original designs. That's fairly typical for the way we go about designing something. In fact, in December of 1943, they released a report, the first progress report on the Eniac, which contained bulk of the designs of the machine. And in that report, there was a discussion of programming. And the figure we see here is a subset of one of the diagrams that was included in that report. The programming in this diagram is for computing the trajectory of an artillery shell. This, of course, was the original justification for building the machine. The form of representation we see here is known as a setup diagram, and it describes the way in which the cables are connected and the switches are set. An alternative way of illustrating things is this setup table. In it, we have the operation of the machine represented in a two-dimensional grid. The rows represent time steps, and time flows going down the page just as modern code does. This two-dimensional representation is not terribly different than the coding forms that arose in the 60s and 70s. The primary difference is that the columns in coding forms are the individual characters that make up the lines of source code. The columns here are a bit different. Imagine, if you will, that you're programming a computer whose instruction set repertoire is only 30 instructions. So what you have is 30 columns in your form. And for any given time step, you go to the column that represents the instruction for that time step and you put the operands into that box. Now, we would tend to think of this as somewhat wasteful, in as much as each time step would only have one instruction being executed and the other 29 columns would all be blank. But in the Eniac, the functional units of the machine could operate in parallel. So a number of these boxes can have something in them, indicating activities happening in parallel on the machine. And instead of instructions, the columns represent the functional units themselves. This form of representation was not at the time called a program, though if we think of it today, it really does fit our modern conception of programming. It determines the control flow. We're ordering steps in time order from top to bottom, unless there are looping operations or some form of conditional operation. The time steps each have some description of what data is being operated on and what kind of operation to perform on that data. It's Essentially, like the old textbook cover used to say, algorithms plus data structures equals programs. So throughout this, I'm going to refer to these things as programs, even though in the day of the Eniac itself, the term program was being used really for something more akin to what we think of as an instruction. By the end of 1943, there had been a certain amount of programming work done, but of course the machine had not yet been built. There was by then a 2-accumulator prototype, and some programming on it, of course, was done for testing. But the larger scale development programs that were kind of motivating the choices of things like how many accumulators and so on, none of that, of course, had been tested yet because the machine hadn't been built. Well, this gets us into 1945. The machine is nearing completion, and a group of 6 mathematicians are assigned to assist with the machine. These mathematicians are women who have been hired and who have been working throughout the war doing manual calculations and using the differential analyzer for trajectory calculations. And what better resource than mathematicians who are already familiar with the problems involved to learn how to solve those same problems on this new machine, and then go on to help other mathematicians, engineers, physicists in deploying their equations on the machine. This group of early programmers, Fran Bilas, Betty Jean Jennings, Kay McNulty, Betty Snyder, Ruth Lichterman, and Marilyn Westkoff, they became, in effect, the first programmers for the Eniac. Certainly the first people assigned the task of being programmers. They had a particularly challenging situation in front of them because they were assigned to this machine before it was completed. So they couldn't really directly use the machine in learning about it. No manuals had yet been written, though they were told a manual was in process. And we'll get to that manual in a few moments. So they had to figure this out based on the engineering drawings of the machine, the untested prototype programming that had been written for reports, and fortunately, to pick the brains of the developers, the engineers, and the scientists who were creating this machine. And collectively, with that information, they were able to develop programming techniques for this machine, and even to develop debugging techniques that anticipate our debugging today. The term we use today, breakpoints, that was coined by this group of programmers. So they were assisting people in learning how to operate the machine. By the time the machine was complete in December of 1945, it was used for a computational problem for Los Alamos. And these programmers assisted the scientists from Los Alamos in deploying their problem on the Eniac. By February of 1946, the machine was now ready for its public debut. So as you might guess, the period between the Los Alamos work and the unveiling was spent developing the code and the programming to demonstrate the machine in that public release, in the press release, and in the public demonstrations of the machine. So this manual that the programmers were told is being worked on was indeed being developed throughout this time by Adele Goldstein. But as you might guess, because the machine was busily being used, completed, used, demonstrated, and so on, Goldstein was unable to test the programs in her manual on the machine. Now, the manual itself was being written during, as I said, this late 1945, early 1946 time frame. We don't know exactly when each of the examples in the manual was first committed to these drawings. When we study the copies of the manual that exist today, we see dates ranging in most cases from 1944 through 1947. Interestingly, the manual was officially released in June of 1946. So those instances where we see diagrams with like revision dates of 1947, it's not clear whether there were later copies of the manual produced with these later drawings, or whether drawings and manual copies have been separated and then later, when people go to scan the copies, find whatever versions of the drawings they can find. But either way, it seems quite clear that the examples developed for the manual were in place, if not before the machine was even finished, at least before its before the publication in 1946 of the manual, and in that time frame there was really no opportunity to test it. When Goldstein's manual was completed and released as a part of the report on the Eniac from the University of Pennsylvania to the Army, this is what the front cover of her part of the report looked like. In recent years, a company called Periscope Film LLC took scans of the manual and republished them in this book right here. And this book, as you might guess, was very heavily referenced as I was developing the simulator. And it is the reference from which I've gotten those examples that I tested on the simulator. Now, anyone who has published code knows that if you haven't tested it before you put it out there, you can pretty well guarantee that Murphy's Law dictates you will have bugs in it. And since it seems quite unlikely that Goldstein was able to test the programs in her book, it probably doesn't come as much of a surprise that there are some bugs in those programs. So we're going to look at one such bug now. This particular bug arises in the example contained in Chapter 6 of the report. Now, Chapters 5 and 6 cover the multiplier and the square rooter. And there is an example that is begun in Chapter 5 and completed in Chapter 6 that uses both the multiplier and the square rooter to calculate this particular equation right here. Now, as you can see in it, there's a square root, there's a division, there are several multiplications, and a number of additions that take place. Now, to understand where the bug arises, we first have to understand that the multiplier does not operate entirely on its own in this machine. The multiplier interacts with a set of accumulators. And in doing so, there are a number of operations that the accumulators carry out that are driven by the multiplier directly. As a result, when we have a setup table, we don't usually draw into the setup table those operations that are happening implicitly as driven directly from the multiplier to the accumulators. So what we see right here is that the multiplier finishes its operation. And when it completes the operation, it causes the result, the product that was computed in accumulator 13, to be transmitted twice into accumulator 12. Now, the reason it's done twice has to do with the way the square rooter works. Not terribly critical, but it is important that it is transmitted twice. Now, if we look closely at this figure, we see in accumulator 12 the operation of it receiving a number twice. We don't see anything drawn in on those same time steps for accumulator 13. But accumulator 14, in the second of those time steps, begins its own transmission of data twice. Now, remember I said that we can have a lot of parallelism in the machine, so there's nothing wrong in principle with transmitting from accumulator 13 to accumulator 12, and also transmitting from accumulator 14, and having those transmissions overlap. Except for one thing. If we look at the way it's wired in this part of the wiring diagram, we see that both accumulator 13 and 14 are wired for their output to go to data trunk 1. So during the second half of accumulator 13's transmissions, accumulator 14 begins transmitting on the very same wires. Needless to say, the result that ends up in accumulator 12 is not twice what was in accumulator 13. It's what was in accumulator 13 plus whatever effect occurs when accumulator 13 and accumulator 14 are transmitting on the same wires at the same time. A sort of wired OR effect. Now, it turns out this is not difficult to fix. Where accumulator 13, it is important for it to transmit twice. Accumulator 14's transmission twice was more a convenience than a requirement. Only the second part of that transmission is actually being used. So it was easy to fix this bug by adding a delay, that is, an extra operation that would hold off a control signal for one addition time, adding that delay before the control to tell accumulator 14 to transmit, and then changing accumulator 14's programming to transmit only once instead of transmit twice. And by making that change, this bug was cleared up. And it turns out in the same problem, a few time steps later, the same bug reoccurs. In this case, it's an overlap again with accumulator 13, but this time with accumulator 15. And of course, the same fix can be applied. And once that fix is applied, then the example computes the value correctly. The interesting thing about this is that the kind of bugs that we find in this early programming are really not all that different from our modern bugs. Now, of course, these aren't the only bugs that we found. There are bugs that are essentially notational in character, that are not unlike bugs we would have today in misspelling a variable or in declaring a variable of one type but using it as a different type. Things that are actually so simple that we let the compiler even point them out for us. This particular bug is more similar to the kinds of bugs that we might have today in concurrency, where I have a shared resource that I'm accidentally using in two different threads of control without having some form of mutual exclusion locking. We don't have to use mutual exclusion locking on the Eniac in this particular case because the timing is so rigid, and we can control exactly when accumulator 13 is using trunk 1 and exactly when accumulator 14 is using trunk 1, and thereby eliminate the conflict without forcing one to wait on a lock. But the feel of the bug, the nature of it, and the sense that the programmer gets as one looks at the code and goes, oh, I see what's happening here, I need to fix this, it's very similar to the kind of debugging experience that one has when debugging concurrent code. Now, needless to say, there are other bugs that were encountered on the Eniac. Many were not documented. But there was one other one in particular whose observation and reporting is worth mentioning. It's almost certain that this bug arose in the spring of 1946, when Douglas Hartree from England visited the University of Pennsylvania and did some work with the Eniac. Later in 1946, in particular in July of 1946, when the University of Pennsylvania hosted what they called a summer school, what has become known now as the Moore School Lectures. On the second day of these lectures, Hartree discussed his experiences and his understanding of mechanized computation. And in it he relates this bug that he had encountered in his programming earlier that spring. And the bug was actually the result of a number being rounded up and then being used as an index into a table. And of course, if you're at the last entry in the table and you have round-off error that causes you to go off the end of the table, well, what happens? Ray-bounds error. And in the case of the Eniac, the tables were such that when you go off the end, you roll back around to the first element. And so he was grabbing, of course, the wrong value out of the table. So it's a bug not unlike what we would recognize today. And when he talked about it, he said the following: having once appreciated what was happening, I saw that I ought to have foreseen the possibility of this situation arising and told the machine what to do if it did. But I didn't foresee it, despite 30 years of experience of computing of various kinds. And this just illustrates how differently a human computer and a machine look at a problem, and how necessary it is for those organizing the application of a machine of this kind to computing problems to get thoroughly accustomed to taking the machine's eye view. One might think that the very earliest bugs in programming an electronic computer would be very different than the bugs we have today. One might think that programming has changed so much since then that none of the lessons then apply. Yet what we find is, as we approach the 75th anniversary of these bugs, we find that really they aren't all that different than our modern bugs, and that the lesson is still the same. That it is vital to be able to take a machine's eye view of the problem. Thank you.